In this lesson, we are going to talk about two concepts. One is about the matrix multiplication, and the other is about the inverse. And you will see that this formula is quite familiar. So let me write it down first. First, matrix multiplication. And the other is, when you have a matrix, you can do the transpose. And this is just another name to say the following identity, which you know in high school. Suppose you have two matrices, A and B. You can take the product. When you multiply A and B and then take the determinant, then its determinant is equal to the determinant of A multiplied by the determinant of B. So I'm not sure, but in my high school, I learned this before. But if not, this is something kind of nice property that should be true, right? It's a good property. And secondly, if you have a matrix, you can do the transpose. You flip the matrix on the 45-degree line, and the determinant of transpose is equal to the determinant of the original matrix. So pretty much this whole hour or 40 minutes, we're going to go through some examples about this, some intuition, and tell you why. Okay, so before we move on, let's think about why it might be true, or what's the intuition of that, right? So recall that whenever we talk about the determinant, one of the biggest thing is that determinant is the same as the volume of the parallelogram, just the volume of the shape, okay? And it has some sign of that. So it is saying that the volume of the shape of AB is equal to the volume of A multiplied by volume of B. Okay, so it would be good. It would be good that we give some example and get some idea of that. So whenever you see an equality, and try to do some example by yourself. Okay, so in this slide, we're going to try to gain some intuition. Okay, get some feeling of that, and it will help you to understand this. And until the end, you will feel like, oh yeah, sure, why not? This must be true. And by that time, you are successful. Okay, so let's think about an example. Let's say we have two matrices. Choose an easy one so that you can calculate its determinant easily. Okay, so you need two matrices, A and B. So just create a simple A and then whatever the B is, and then try to calculate what is the AB. So you'll notice that the only difference is that the first row is replaced by 3 times of itself. And you can imagine that this is A, and this is B, and this is A times B. And it's not hard to calculate its determinant. You can just do it by yourself, but I believe this is 3. And what is this? Let's try to do a simple calculation, okay? You don't have to write down this, but you should be able to know, to calculate what's the determinant, okay? Okay, sorry. Then it is 2. And you can try this again, or just pop up any program that I've been showing you. You can use program to calculate something. And supposedly this one is equal to 6. Okay, so this doesn't really important. You can do it by yourself. Okay, so yeah, then you do some example and realize that yes, this is the equality. A and B and then AB, their determinant is following the formula. But now what, right? So try to think of what you can say about these things. Say for example, this determinant is equal to the volume of the shape of this one. You have 1, 1, 1. And then you have another quantity that's here. You've got 1, 2, 3, right? And you got another dimension which is 1, 4, 9, and you can use that to create some shape looks like this. The line is very vague, but it's something we call that as parallelotope, 平行六面体. And that's the volume of this one is equal to 2. That's the main idea. Okay, now if you have something like this, 3, 3, 3, 1, 2, 3, 1, 4, 9, you notice that the second row and the third row does not change, right? So you can draw the same picture, and you don't really do that on the paper, but you can do that in your mind. You have 2 vectors that stays the same. But somehow the first row is replaced by 3 times of itself. Okay, so if you draw the shape, you can notice that this one, this parallelogram, 平行四边形, this one is replaced by this one. And this one is exactly 3 times of this one, right? The base is 3 times of the base of here, and the height is the same. So the base of this shape is transformed into 3 times of itself. And now you simply make it taller, and you will see that the volume is also multiplied by 3. And this 3 is this one. So the idea here is that whenever you multiply by a matrix, the matrix is more like do some transformation to the shape, and the shape will change its volume accordingly. But what is the rescaling factor? 这个转换的体积的比率是多少? And this scaling factor is exactly the determinant. So this is what I'm trying to say. determinant can also be viewed as the scaling factor, 转换的系数。Okay, any questions for this part? Okay, try to run this kind of simulation in your mind, and time by time you'll feel like you get more feeling about the mathematical object, and it will help you in general in the long run. Otherwise, a formula is just a formula. It doesn't help you too much, right? Okay, so whenever you multiply by something, the shape will also be changed. But how much it will be changed? What is the exchange rate from left to right? It is exactly the determinant of this this matrix. Okay. Now, then let me say something else. I'm not sure if you encountered this already, but there is something called Jacobian in calculus. I write it on the side, just I want to let you know there are something that is related. Often you have to do the integral over, say, dx dy, and you know when you are doing the dx dy, it is calculating the area, right? You are calculating the area or something, and you know you can do the change of variable. I'm not sure if our course already get to there. You can change that to the polar coordinate, 极坐标, right? You know, dr d theta, but this is not the right formula. You have a dx and dy, and you have dr d theta, but they are not equivalent. The reason is the shape of dx dy is different from the shape of dr d theta. And the thing is, the thing is that this side is not d theta. This side is r d theta. But that's not my point. My point is that when you do the change of a variable, you have to add something in the front. And in this case, it is r. It is a particular r. Let me double check. Have you seen this formula for calculus? R dr d theta? Okay, then forget about that. But what I'm trying to say is whenever you want to change this one to this one, the volume also changed. So you have to add some factor here, and the factor here, for the simple formula, the calculus textbook will provide you a formula. But in general, you have to calculate the difference between dx dy and dx dy and dr d theta, and this one is done by determinant. Okay, so ignore that if you haven't seen this before, but just try to let you know, in calculus, you have to use this kind of technique to transform the difference between two variables. And so this idea will help you to learn how to transform the rate of the volume. Okay, so let's give a basic proof of that. Recall that we are trying to say that determinant of AB is equal to determinant of A times determinant of B. So the key is that, I'll write it here. The key is that if you have A written as the product of several elementary matrices, then the determinant of A is done by the determinant of all of these elementary matrices. Recall that the determinant of the elementary matrix can be -1 if you swap the two rows, and can be 1 if you just add one row to the other row. And you can also have rescaling. If you multiply a certain row by k, then the determinant is equal to k. So you have to record all these things, and in the end you got the determinant of A. So if you have such a thing, then you got the idea. So now let's write down the proof. So at the beginning, suppose both of A and B are invertible. Because invertible matrices are good, they can be written as this form, right? So then A can be written as certain form, and B can also be written as a product of elementary matrices. Moreover, whenever you write it like this, you know the determinant of A is exactly equal to the product of these determinant. Well, if you accept this setting, then it is super easy afterward, because you got A and B, you have a basic setting. Then you can try to think of what is A times B. Then you will realize that, okay, this proof is just a lot of writing, but it's not too hard. Okay, A times B can also be written as the product of several elementary matrices. If my writing is not so clear, kindly let me know, okay? I try to make my writing more upright and clean, but I tried. And the thing is, if you are able to write it like this, A times B, then the determinant of this guy is equal to the determinant of this times determinant of this, and multiplied by everything. So in the end, it just they are the same. So by definition, recall that the definition of determinant is you just do a lot of row operations, and then try to record everything, right? And they are recorded by here. So you know that this guy can be represented as a lot of this, and try to do all the coefficients here. So the determinant of AB is equal to the scaled-in factor of all the elementary matrices. Like what I say is a lot of writing, so the important part is not really just write it down or remember the process. It's try to think clearly why we have to do this, right? And which part is the definition, and why this argument work. Otherwise, you will feel like we just get it wrong and say a lot of weird things and then come back. 尤其在一年级的数学啊，一年级的数学你常常会遇到说，我们到底在搞什么东西？那你会觉得好像绕了一大圈啊，然后写了一大堆废话，然后最后得到你本来就应该要知道的结果。那重点在于说，你要想一下为什么要绕那一条路，就是 A 为什么要把它写成这个样子？原因就是因为我们在定义行列式的时候，这个它是一步一步走的，那所以你一步一步走就记录在 F 里面 ，B 也是一步一步走。那你把 A 和 B 的一步一步走全部的合在一起的话，那你就可以把 A、B 的这个列运算的一系列的东西把它记录下来。Okay, if you have questions, just let me know all the time. Okay. So now you see what is the first case. The first case is when both of them are invertible. So the second case, you have to take care the case that when one of them is not invertible. If this is the case, then either determinant of A, well, let me write it in a different way, sorry. So recall that if it is not invertible, then the determinant is equal to 0. So this is actually the easy case. So one of determinant of A and the determinant of B, one of them is 0. As a consequence, the product of that is equal to 0. Also, if you think about AB, if one of A and B is not invertible, then A times B is not going to be invertible. So it is also not invertible. As a consequence, the determinant of AB is equal to 0. But you have to be careful that you have to think about why this is true, right? If AB, one of that is not invertible, then AB is not invertible. That's something that you have to think it clearly. All right, so if this is the case, then you will see that the product and the determinant of AB, both of them are 0. then the proof is done because both sides is equal to 0. Okay, so like what I say, you need to think about why we need to do this instead of just remembering all the steps. And then otherwise, you will feel very painful to remember a lot of things. Now, second step is pretty much following the same idea. We want to show that the determinant of AT is equal to determinant of A. And quite unfortunately, for this identity, many people know it is true, but up to now, I haven't heard of any good explanation of why it is true. You can give a proof, and yes, it is true, but there's no geometric meaning, or at least I don't know. But in order to prove that it is true, it is very simple. The key is, again, when I say key, is something that you don't need to write that in the proof. Okay, so the key is that for elementary matrix, if you have an elementary matrix F, then the determinant of F transpose is also a F transpose is also an elementary matrix. So if you check that carefully, then you will realize that, okay, no matter it is swapping the row, rescaling the row, or adding the multiple of a row to the other row, each of the three categories, the determinant of F transpose is equal to the determinant of F itself. So the rest of that just following the same philosophy that you can get it through. Okay, so suppose A is A is the product is invertible, and you know the other case is suppose it is not. Okay. Then again, A can be written as the product of several elementary matrices. And you know, doing the transpose, just following the same philosophy, you're doing the transpose. But when you do the transpose of the product, K will be in the front, and then go back to F1. So be aware of the order, okay? So the rest of that is you can try to finish that. The determinant of AT is equal to the determinant of all these quantity. I guess I don't want to write that, and you don't want to write that either. It is equal, let me just write it one. The determinant of Fk transpose. And in the end, you will have that equal to determinant of F1, of Fk without transpose, and it is equal to the determinant of A. So that's the same philosophy. Try to do the same thing. And the other case is when it is not invertible. This is much easier. Then A transpose is also not invertible. So determinant of A and the determinant of A transpose, both of them are equal to 0. And the identities still work. I know I put a lot of information in at once and go through a lot of things in a rush way. But lastly, let me say a few things of why we care about the volume of the row parallel top. Recall that previously we talked about using the row to generate the parallel top and the columns. 我们用行和列分别去产出那个平行多面体。Okay, and so we know that this guy is equal to the volume, the row volume of A. And we also know that the row volume of A is equal to the column volume of A. This is not trivial, but according to the definition, they have the same quantity. But now, if you think of the determinant of A transpose, then it is equal to the volume R of A transpose. And whenever you do the volume R on A transpose, it is equal to the volume C of A. So basically, this identity is equivalent to these two, saying that whenever you check the columns and the rows, the volume generated by the columns and generated by the rows, they are going to be the same. And it's not so obvious why it is true, but according to the proof and lots of things, then it is that way.